Computation is often associated with symbols, notation, and formal rules. This association reflects later developments rather than historical necessity. Long before algebraic language or proof-based system was stabilized, certain cultures built devices that enforced numerical relationships directly through material constraint. These devices did not reason. They did not represent logic explicitly. They behaved correctly because deviation was mechanically restricted. The Antikythera mechanism is the most complete surviving example of this mode of computation. This is before logic, a history of rules before they were written. The Antikythera mechanism is known only through fragments recovered from a shipwreck dated to the early 1st century BCE. The vessel sank near the island of Antikythera in the Aegean Sea, carrying luxury goods, statuary, and objects associated with elite Greek material culture. Among these remains were corroded bronze fragments whose significance was not immediately recognized. For decades, they were treated as debris. Only later examination revealed that the fragments once formed a coherent device with internal structure, precision components, and engraved inscriptions. The mechanism does not survive intact. Its interpretation depends on reconstruction from partial evidence, imaging techniques, and comparative astronomical knowledge from the Hellenistic period. The mechanism consists of interlocking bronze gears housed within a wooden case. Surviving inscriptions indicate that it was designed to model astronomical cycles. The front face likely displayed the positions of the sun and moon relative to the zodiac. The rear contained spiral dials corresponding to longer-term cycles, including the Metonic cycle governing lunar months and the Saros cycle used to anticipate eclipses. These cycles were not discoveries of the mechanism itself. They were established components of Greek astronomical knowledge, derived from Babylonian observational traditions and adapted within Greek mathematical frameworks. The mechanism did not generate new theory. It encoded known periodicities into a material system that enforced their relationships mechanically. The gears vary in size and tooth count. These ratios are not arbitrary. They correspond to numerical relationships between astronomical cycles. When a user turned a crank or dial, the motion propagated through the gear train, producing synchronized rotations across multiple outputs. Each output represented a different cycle. The system thus transformed a single input into multiple constrained results. The manufacturing of these gears represents a specific technical threshold. In the Hellenistic period, cutting bronze teeth by hand to a uniform pitch required sustained precision. Minor irregularities in spacing or eccentricity would introduce friction and misalignment. Because the mechanism transmitted motion through long sequences of interdependent gears, small deviations would accumulate rather than cancel. In such a system, an initial error does not remain local. It propagates across stages, increasing resistance and degrading motion until the device no longer functions reliably. The existence of a working mechanism therefore implies a production process capable of anticipating cumulative mechanical error and minimizing it through consistent fabrication. This indicates disciplined workshop practice rather than experimental assembly. The device does not calculate in the abstract sense. No numerals are manipulated during operation. No rules are applied sequentially. Instead, constraint is embedded directly into material form. The gear ratios embody arithmetic. The linkage embodies dependency. Once constructed, the mechanism cannot deviate from its encoded relationships. The device does not check its own results. It does not adapt. It does not infer. It behaves consistently because deviation is mechanically restricted under normal operation. Perhaps the most technically complex feature is the probable inclusion of a differential arrangement used to model lunar irregularity. This configuration allows one rotational cycle to be offset against another, producing a derived motion corresponding to the synodic month. Such an arrangement does not merely transmit motion, it transforms it by enforcing a relationship between competing cycles. The transformation is continuous and automatic. The subtraction is not displayed as an operation. It is embedded within the mechanism's structure. The observer encounters only the resulting motion, not the process by which it is produced. This separation between internal complexity and external output represents an early instance of constrained transformation realized entirely through mechanical means. This form of computation differs from later symbolic methods. Greek mathematics at the time emphasized geometry and proportion rather than symbolic manipulation. Proof existed, but it operated within abstract discourse, not within instruments. The mechanism does not rely on Euclidean demonstration. Its correctness depends on fabrication accuracy and adherence to known cycles. If the ratios are correct, the output follows. If they are not, the system fails without explanation. The Antikythera mechanism demonstrates that complex computational behavior can arise without formal logic systems, algebraic notation, or proof-based mathematics. Its behavior is deterministic, repeatable, and independent of interpretation once constructed. These properties are characteristic of computation understood as constraint satisfaction rather than symbolic reasoning. The inscriptions on the device suggest that it was accompanied by explanatory text. These inscriptions appear instructional rather than theoretical. They describe dial functions and expected outcomes. This implies that the mechanism was intended for use rather than display. Operation required limited interpretation. The user did not need to reconstruct astronomical theory to obtain results. Knowledge was externalized into structure. This externalization marks a significant development. Knowledge no longer resides solely in texts or trained practitioners. It becomes embedded in artifacts that enforce correct relationships by design. Error reduction occurs not through improved reasoning, but through restricted operation. The mechanism reduces dependence on judgment by substituting physical regularity. The existence of such a device also clarifies the fragility of technical continuity. The Antikythera mechanism appears to have been produced within a narrow convergence of astronomical knowledge, precision metalworking, and economic support. These conditions were not permanent. When trade networks, workshop specialization, or patronage structures weakened, the capacity to reproduce such devices disappeared. The loss does not reflect conceptual inadequacy. It reflects the collapse of the material and institutional conditions required to sustain precision fabrication. The mechanism's disappearance for many centuries illustrates a general property of complex systems. Technical capability does not persist automatically. It depends on surplus resources, stable transmission of craft knowledge, and sustained demand. When these supports erode, even well-understood techniques can vanish from practice. What remains is evidence that computation does not originate with symbols or formal logic. It emerges wherever relationships are stabilized into systems that behave consistently under constraint. The Antikythera mechanism demonstrates that analog computation can exist without formal computation theory. It shows that logical structure can be imposed materially without explicit logical language. The device does not think, it does not reason, it does not interpret its own output, yet it produces structured results aligned with astronomical cycles over extended periods. Its reliability derives from imposed structure rather than understanding. In this respect, it occupies a boundary position between observational knowledge and mechanical execution. The Antikythera mechanism should therefore be understood not as a precursor to later machines, but as evidence that constraint-based systems can exist independently of formal logical frameworks. Its significance lies in what it demonstrates about the relationship between knowledge, material precision, and enforced regularity. In the next episode, we will examine Babylonian algorithms and the emergence of procedural knowledge before formal theory.